At the beginning of this topic, we found integrals by finding areas of triangles and trapeziums and rectangles and those kinds of things. And we introduced the concept that it was an approximation. The ones that we had, if they were nice straight lines, they were exact, but we could also use it as an approximation, which is what we're going to be doing today. Now, this method is called the trapezoidal rule because it makes trapeziums. That says sometimes we are not able to integrate. Therefore, there are methods that may be used to approximate the definite integral. One of these methods is the trapezoidal rule. Sorry, I just got a tickle all of a sudden. This rule considers the area under the curve to be the shape of a trapezium, and we know the formula for a trapezium is this one. You're teaching the class, Charlotte. Okay, the trapezoidal rule is in this diagram down here. You can see that we have a curve, but we're making a trapezium between A and B. So we say that the integral of that function between A and B is approximately equal to, notice that symbol, and we have this formula, which is an adaptation of the trapezium formula. The B minus A is the height of that trapezium across here. It would be the H in our normal trapezium formula. So this is the H, and this is the over 2 part, so H over 2. And then these parts, f of A plus f of B, f of A would be the length of that side. And f of B is the length of that side, which are the two parallel sides of your trapezium. Can you see that that is your trapezium formula? This is H over 2, bracket, that's the A plus B, but it's in function form. Okay? So, there it is. Now that is what we call for one sub-interval. We've made one trapezium. We are going to adapt that to have multiple trapeziums, but not just yet. So it says, always start a trapezoidal rule calculation by constructing a table of values, which I'll be showing you how to do. Also remember that depending on the concavity of your curve will depend on whether you are overestimating or underestimating your area. If the curve is concave up, like this one, then the trapezoidal rule, your estimate is going to be bigger than the real one, right? Because the real area is cut off down here, but you're actually saying it's up here at this straight line. Your calculation will be over the real one. Whereas if the curve was concave down, that top line would be underneath your curve, which means that you are underestimating the integral. And if the curve is linear, so straight line, then you should be able to get an exact value for that area. So here is our first example where we are finding an approximation for the integral between 1 and 6 of the dx on the top. You can move to the side, so it's really 1 over x dx. 1 over x is our function. It says use the second derivative to explain whether the approximation overestimates or underestimates the integral, but one bit at a time. There's a few things in there we have to do. So first thing it said in capital letters was that we have to make a table. The table has the x values that you are going to use and the y values. Now this in here, I said to you before, that dx is kind of in our way. Just imagine sliding it over to the side and my equation would be 1 over x. That's basically the function that I'm working with here, y equals 1 over x. Because I'm only making one trapezium, so one subinterval, one trapezium, the numbers that are on your integral sign are the numbers that you have to put into your table. So I'm going to have two things here. I'm going to have 1 and then I'm going to have 6. And I need to find the y values that correspond with that by subbing those into this rule that I have here. So if I sub in 1, 1 over 1 is 1. If I sub in 6, I get 1 over 6. Okay, we have the table first. Now we're going to use our formula that was in the box. The integral of 1 over 6, from 1 to 6, of 1 over x dx is approximately equal to. Now the formula, maybe I should shrink this down so I can see it, is up there in the yellow. It is half bracket b minus a. What is the b and the a? They are the numbers from your integral sign. So b is the top number, a is the bottom one. So it's 6 take away 1, close bracket. Then we have square brackets, and the formula says f of a plus f of b. The f of a and the f of b are these y values here. So it's 1 plus 1/6. Okay, and then you just type that into your calculator. Has anyone gone ahead and done that? 2 and 11 over 12. You don't need to use square brackets when you're typing that in. You can just use 2 sets of round brackets. Everyone okay with that? Okay. Now, please notice just a little bit of setting out. You use an approximately equal to for the first one, but normal equal to after that. Okay, because this one is exactly equal to this line here, but this is approximating the area under my curve. Okay? All right. So I have done the trapezoidal rule, but the second part of the question said, use the second derivative to explain whether the approximation overestimates or underestimates. The second derivative talks about concavity. This is saying, is this curve concave up or concave down? Because that tells me whether I've overestimated or underestimated. That's this stuff in here, concave up, concave down. Okay, so differentiating practice. My original curve was 1 over x, but if I'm going to differentiate it, I'm going to call it x to the minus 1. Bring it up so it's ready to differentiate. Y dash, and this is very important that you don't confuse your integrating with your differentiating. We are differentiating, which means the power comes down the front, so minus 1, x, and then you subtract 1 from the power to become a minus 2. Then I want to go to the second derivative, so I do that again. Y double dash. Multiply your minus 2 down the front will become a plus 2. Keep the x, subtract 1 from the power makes a minus 3. So that form is okay, or you can put it back into fraction form if you want to see your final answer like that. So 2 over x cubed. Now, is that curve going to be concave up or concave down? We are only looking at x values that are above 0. We're going from 1 to 6. We're positive values of x. If I put positive values of x into here, am I going to get a positive answer or a negative answer? Positive. There's no minus signs in here. Even though it's cubed, cubing positive numbers stays positive. 2 divided by a positive number is still positive. So I'm just going to write down here that when my x values are greater than 0, because that means positive, my second derivative is also greater than 0, which is positive. Does that mean my curve is concave up or concave down? Concave up. Excellent. Therefore, concave up. And look back up to the little note above. When it is concave up, are we overestimating or underestimating? Overestimating. So therefore, our approximation is an overestimate. Okay. So that was one trapezium. Over the page, for more accuracy, when finding the area under a curve, it is possible to break the area into more than one trapezium. The more trapeziums we have, the less gap we're going to have between our trapezium line and the actual curve. More trapeziums means closer to the actual area. Okay, so here is a formula for adding up all of the trapeziums. This one's got lots of little sections in here. All of the trapeziums you could possibly want. So here is our integral again. It is approximately equal to the height of your trapezium, which is this one little space across here. So in there, h. One of those little spaces, that's your height. Your height over 2. Your first and your last y value. Okay, you've got all these vertical lines. Your first one will be here and your last one down here. And then you need 2 lots of all the little ones in between. Because if you think about your trapeziums, if I do that trapezium followed by the second one, I'm using that line twice because I'm using in the first trapezium and the second trapezium. Does that make sense? So it's adding them all together for me. There is a little note there on how to find h. H is your b minus a, so the numbers on your integral sign, subtract them and divide by n being the number of trapeziums that you are trying to break it into. We call them subintervals. Okay? So one subinterval or one trapezium or one strip, that's what the n is. Now this formula I think looks a bit crazy. This is a bit of a shortcut to the trapezoidal rule down here. Instead of all the y, 1s and 2s and whatever's in there, we just say the width of the trapezium over 2. E stands for the ends, the 2 ends. You add the 2 ends together, plus 2 lots of m for all the middles. Okay? You will not see this on your formula sheet, however. Okay? That's a bit of a, helps you memorize, but not something that's ever going to be on a formula sheet. So let's try and do a question with 2 subintervals. Question 2. Find an approximation for the integral of x squared between 1 and 4 using the trapezoidal rule with 2 subintervals. So, because there's 2 subintervals, I'm going to start by working out, I'll call it W because I'm going to use the second formula, the width formula. It's the same thing as the H though. You subtract the numbers on your integral sign, 4 take away 1, and you're going to divide that by 2 because you want 2 trapeziums. So you're dividing it into the 2 trapeziums. That is equal to 3 over 2, or 1.5. Now we need to make up our table so that we know all the y values. We have x's here, y's there. The first value you will have is the lowest number on your integral sign, which was a 1. Then the next x value, you add on this 1.5 onto that. 1.5 plus 1 is 2.5. Then you add on 1.5 again. What's 1.5 plus 2.5? 4, which is perfect because 4 was the number that I had to get to. So think of those 2 trapeziums. If you think of 2 trapeziums that look, you don't have to draw this, but here is my curve, and I've got between 1 and 4, I'm splitting that in half, and that line in the middle is at x equals 2.5. Okay, it's that middle row of my 2 trapeziums. Okay, now I need to find all the y values. I sub these into where? Up here, this x squared, the little function that's sitting here in my integral. So x squared. 1 squared is 1. 2.5, which is 5 over 2, squared, 25 over 4, or you can do it as a mixed numeral, that's fine. And then 4 squared is 16. Okay, this is why you always have to do this first so you're ready to put it into your formula. So here is my original integral. It is going to be approximately equal to, do you want me to, I'll write the formula down. The width over 2, I want the ends plus 2 lots of the middle. Okay, that's my shorter formula. So the width we worked out was 3 over 2. That has to be divided by 2, open bracket. E stands for the end values, which is the 1 and the 16. So I need 1 plus 16. And then I need 2 lots of the middle. If I've used these already, there is only one thing in the middle, which is the 25 over 4. So 2 lots of 25 over 4, close square brackets. And typey, typey, type. You just want me to write it down, don't you? You just want me to write it down. So I got 22 and 1/8. You got the same thing. It's beautiful. Okay, let's just do that a few more times. Question 3. Ready to keep moving? No, wait. You good? Okay. Question 3. Find an approximation for the integral of t squared plus 4 between 0 and 12 using the trapezoidal rule with 6 subintervals. At least the question will always give it away. It'll say trapezoidal rule, okay? So as soon as you see those words, this is the process that we do. Now, 6 subintervals. First of all, let's find our W. To do that, we subtract the numbers on our integral sign. 12, take away 0 over 6. 6 subintervals. The n on the bottom is the number of subintervals, which is 6. The answer of that is 2. That's what you meant, wasn't it? Yeah, of course. Okay. Then we need a big table because we need to have all of our function values. So we're starting with x is 0, and we're going to have a whole bunch of them. Now, it's going to be, we're starting at 0, and as we go across, they're going to be going up by 2. That's why you need this number first, okay? So 0 plus 2 is 2, plus 2 is 4, plus 2 is 6, plus 2 is 8, plus 2 is 10, plus 2 is 12. And I've stopped at 12 because 12 is the number here. The other thing that is a good check, if the subintervals are the number of trapeziums, when I did 2 trapeziums before, there was 3 numbers here in my table. When I did 1 trapezium, there was 2 things in my table. The number of function values, the number of y values across here is always 1 more than the number of subintervals. So I had 6 subintervals, 1, 2, 3, 4, 5, 6, 7. There is 1 more. Okay, so it's a bit of a check to make sure you've got everything spaced out properly. Now let's go through and let's do T, because we're using T. All right, let me change my letter since we're just using T instead of X, that's okay. Sub these into here to find the y values. So it'll be 0 squared plus 4, which is 4. Next one, 2 squared plus 4 is, yes, 8. 4 squared plus 4, 20, good. 6 squared plus 4, 40, good. 8 squared plus 4, 10 squared plus 4, 104, and 12 squared plus 4. 148. Well done, you people doing that in your heads. Good job. Okay, let's find our integral now. So between 0 and 12 of t squared plus 4 dt, we are approximating that, so approximately equal to, and our formula again is w over 2 ends plus 2 lots of the middle. So the w for this question is 2, so it's 2 over 2, open bracket. The ends means the 4 and the 148, the two end values. Plus 2 lots of all of the middle ones. So that means that one, that one, that one, that one, and that one. They are all the middle ones. So put it in brackets. 8 plus 20 plus 40 plus 68 plus 104. Close the round bracket, then close the square bracket and type it all in. Yes, great, well done. All right, one more to do. We probably didn't need a full page for that. Anyway, over the next page. All right, guys, focus, please. Last question. Find an approximation for the area of the following. And this one's a little bit different because there's no integral sign in there, no function to sub into. Instead, the diagram is actually giving me all of the information on the diagram. These vertical ones, they are my function values. This one will be my first, this one will be my last, they're my three middle. The width I can get from going across here. Each of these numbers are going up by 1, so that will be my width. So let's just write that down. My width is equal to 1. You can rewrite that information into a table if you like. You don't really need to. Most of you can probably read it straight off that diagram, but we'll stick to our process, which is to fill in a table. So x values, y values. The x values are 0, 1, 2, 3, and 4. And the y values, as I said, are just these numbers here. So at 0, it's 3.7. At 1, it's 5.9. 2 is 6.4. 3 is 5.1. And 4 is 4.9. So I don't have an integral sign to write down here. So I'm just going to say A for area, because it said find the area, is approximately equal to width over 2 bracket ends plus 2 lots of the middle. And let's just do that straight from our table. Our width was 1. The ends are 3.7 and 4.9. Then we need 2 lots of all the ones in the middle, which is 5.9 plus 6.4 plus 5.1. Close up all your brackets. And that equals 21.7. Do we have units? Yes, we do have units. We could put meters squared on there. Look at that. Well done. The last one, did it have units on it? You could put units squared on it. Not for that one, no. Okay.